Mm. It's almost there. Yes. Okay, so
path from the bottom of the grid to the top of the grid, or vice versa.
okay, let me share my screen now. Okay. Okay, so let's start. So today's topic is parameter estimation. Okay, so we will be, let me tell you what we are going to discuss in a very general way. So let's imagine a very simple experiment. You have coin tosses, right? You have a coin, it could have heads or tails. So your sample space is just heads or tails, which means each experiment or each trial will give you either a heads or a tails. Let's say the probability is like this. Probability of heads, or you can say probability of x being equal to heads. Probability of x is, let's say, 0.4 for heads and 0.6 for x equal to tails, right? So this is the distribution, which means every random flip you make, you will get this kind of distribution. Now, what does it imply physically? What does it imply physically? So physically, it means if you do this experiment multiple times, let's say if you do it 100 times, then you obtain samples. So remember, this is called sample space. Right, this is the sample space. This is your probability mass function, PMF, this P. And what is x? X is a random variable. X is a random variable. Now, if I run this experiment multiple times, let's say I run it 100 times, I will be getting samples of x. Let me denote them by S. I will say S0 is a heads, S1 is a tails. Another time I flipped it, S2, I got a tails again. In this way, I'll keep going. So what are these? These are the samples. These are the samples. So keep in mind the difference between the random variable and samples. Random variable is a variable and it has a distribution, but samples are the exact observations which have been made. So let us say I run this experiment 100 times, I will get 100 samples. So let us say I run it 100 times, this means I will get Si for I equal to 1 to 100 or 0 to 99. These are my all the samples. This is my sample set. All the samples are there. Now, what does this mean physically? That 0.4 and 0.6. It will mean, okay, intuitively, almost 40% of these samples will be heads and almost 60% will be tails. It means, okay, it could be 59 and 41, or it could be 39 and 61, or maybe with more or less variations. But the larger the sample size I will take, the larger the size I will take, the closer my observations will be to these numbers. Like if I take 10 to the power 5 samples, then 4 into 10 to the power 4 approximately will be heads, and 6 into 10 to the power 4 approximately will be tails. Like that. So that is the meaning of sample space. Can you think of, let me inspire some practical thinking from you, from your side. Can you think of some practical scenario where this kind of sampling will be useful? Let me start with one example myself. Okay, let me first give you a chance to think, so that I want to see if I want to see your thinking. I'm sure you will bring many new perspectives into the whole picture. Could you please write on the chat window some practical applications of this probability distribution and sampling from there, probability density and sampling from there. It could be discrete or continuous, like that. It could be any. One example I can give. If I pick, let's say, if I pick 100 people in India, what will be the probability that they have corona? Out of 100 people, what is the probability that they have corona? Now, this number can give me an idea how many people in India are affected by corona, right? Because let's say out of population of India, 10% people or 1% people are having corona. Then this probability, if I estimate that, if I have, let's say, how many samples I have here. Let me, so I'm now giving one example here. So I will split this space like this. Let's say I make observations. I want to estimate. So what is my random variable in this case? I want to estimate how many, if I randomly pick 1,000 people, how many people will have corona in India. So what is my sample space here? What will be my sample space here? S is equal to, what is my sample space? Please give answers, don't feel shy. Sample space is, okay, I think this is a difficult question. No, it's not difficult, just think carefully. Yes, Shivam has given correct answer, that it is positive or negative. Jason there has said yes or no. Yes, they are. So it's a binary set, which means it has only two samples, corona positive or negative. Let me call it as Y and N, corona yes or corona no, positive or negative. Or I can also call it as positive, negative, anything. Okay. And now what is my PMF? Probability of X is equal to what? I don't know. How do I estimate it? This is the random variable. X is the random variable which corresponds to whether a person will have corona or not. Now, see, X is a mathematical quantity. It is not directly a number. I mean, X is a probabilistic. It's a random variable which can have different values, but it doesn't have one specific value. But samples are specific values which have been observed already. You took one person, you saw he has positive, so you will, this sample is positive. This is a sample. This is not a random variable. This is a sample. It's an observation. But random variable is a variable. Sample is not a variable. Sample is a definite value. Okay. Tell me. Okay. Now I don't know. I don't know what is the value. I know it will be a distribution like this, where when my X is positive, it will have some value. When my X is negative, it will have some value. But I don't know what are those values. Right? This is called parameter estimation. This probability mass function, or in general probability density function, will have some unknown quantities which you have to estimate from the data. This is called parameter estimation. So this is a binomial distribution, binary distribution, where you will have two values and each has a probability p or 1 minus p. So if I call this as p, then this will be 1 minus p. So how many parameters are there which I have to estimate? Tell me in this example. How many parameters are there which I have to estimate? Write on the chat window. 1. Yes, very good. There is only one variable, not two. Only one parameter has to be estimated. What is that? That is p. Because the other one is, of course, 1 minus p because they should sum to 1. So I have one parameter which I have to estimate. Now question is, how do I estimate it? Can somebody write on the chat window? How do I estimate? Okay, I think Divyajyoti went one step further. Come back. First, what will you do, Divya? If I ask you, uh, uh, go out and find out the value of P. Afzal is very close. Shivam is very abstract. Afzal says count the number of positive S. That is not complete answer. Shivam says experiment. Okay, what kind of experiment? Afzal is very close. Yes. So Shashwat gave the complete answer. You have to not only find positives but also negatives, or in general, you have to find total number of observations. So you have to collect samples, right? How do you find out these parameters? You collect samples. Collect samples. What are samples? Samples are the observations. So let us say I looked at one person, whether he's positive or negative. I found, okay, he's positive, dangerous, stay away. Another one, negative. Another one, negative. Another one, like that. I can keep going. So this is how I do sample collection. Now, from these samples, I have to estimate the value of the parameter p. So, yeah, let me call it as p and 1 minus p. Only single parameter. Now, question is, what is p? I'm just writing for completeness. So you collect samples. And after collecting samples, from these samples, you have to estimate the value of p. So in nutshell, this is the problem of parameter estimation. So you have some samples. From these samples, you can compute the histogram or you can compute the model, like that. Anybody has any questions at this point? If you have watched the videos, if you have seen those videos, I think now you will be able to relate it with real life. It's very important to relate your theory with real life. I hope you can do it now. Anybody has any questions, please ask. Otherwise, I'll give one more example. I can give you one more example. Somebody would like to tell me what example can we take? Give me an example of a continuous random variable. So this was a discrete random variable. X was a discrete random variable. It could have only discrete two values. But if I have a continuous random variable, it can have continuous values from a continuous set, basically. Your sample space is a continuous space, continuous set. Now tell me an example which we can discuss. Count the number of positive cases divided by total number, temperature of a city. Okay, temperature of a city. Yes, temperature of a city is a good example. It's a continuous variable and you can estimate it very well. Yes. Time. What time will a particular flight reach the destination? Yes, very good. Weight of people. Yes. If I'm in India, I pick up a random person. What will be his weight or her weight? So that will have a distribution. So let us say in a country where people are overweight, your distribution will be more towards right-hand side, and a country where people are underweight, distribution will be more towards left-hand side. So this, let's say this is the weight. This is a random variable weight. These are not samples. These are random. This is a random variable. And this is the PDF, probability of W. Okay. So let's say this is a country which is more overweight. This is a country which is underweight. And this is a country which is normal, means which is a healthy country, healthy people. Okay. This was a good example, weight. This has one constraint. What is that constraint? Weight is 0, weight is 100. Weight cannot be negative, right? Keep in mind this constraint. The weight cannot be negative. If you get a distribution like this, then means a distribution like this, then it is giving some probability to also negative weights, which is not possible. This will not be a valid distribution. So you either choose your, okay, we'll come to this later. Okay, now if I want to estimate the weights of people in a country or in a locality, what will I do? What will I do? I want to make a model. So let's say in the previous example, this was my model, and this is a very good model. It does the binary classification or binary random variable modeling very well. Let us say now this is my don't consider this. I want let me. So I define my problem. Problem is I want to estimate the weights of people in a particular locality. Let's say in our class. Okay. So what will be your strategy? First of all, number one, choose the model. Okay, the problem, let me first write down just for sake of completeness. Problem is W is weight of a person. Find probability density function, PDF of W in a locality. Okay, so this is the problem. Now, what is your what is your approach? Number one, we have to like what we do here. First, we chose a model, right? We decided this is the model which we are going to use for modeling this distribution, and this model has got these parameters, and we collect samples to estimate these parameters. So what is the weight of a person in a locality? One, choose a model, or just choose a model means, or what do you say, select a model. And second is collect samples. Third is estimate parameters. Using the samples. Okay, this is the approach which we take. Now, first I select a model. So what model should I use? How do you know? The answer is, first of all, so you have to swap these steps. First, you collect samples, right? Then you look at those samples. How does it look like? Then you select a model, and then you estimate your parameters. Is this point clear? I think this is a very subtle point which I'm mentioning, that don't select the model before looking at the problem. First, you look at the problem, look at the data, how it is distributed. This gives you some idea of the distribution. Then you select your model, and then you estimate your parameters. I'll give you an example. Let us say you are trying to model weights of persons in a locality. Let us stick to this problem for some time. So what do you observe? You get the samples. Let's say your S0 is how many? 60 kgs. S1 is 65 kgs. And in this way, you keep going. Now, looking at this data, you have to choose a model. What kind of model can you choose? So a very good way of visualizing the data is you take a histogram of this data. What is histogram? Histogram is a kind of you make windows of weights. Let's say weight can vary between 0 to 100. You make windows. This is 50. This is 75. And this is 25. And you have all this data. You plot a histogram. What is a histogram? W is a continuous random variable. You discretize it into discrete random variable and choose your bins appropriately. So let us say these are my bins. So a continuous random variable, you discretize into a discrete random variable by binning. Because this is a single random variable, it's very easy to choose your bins. I have chosen my bins from 0 to 100. Let's say how many? 1, 2, 3, 4, 5, 6, 7, 8. 8 bins I have chosen. Now I will start putting these samples into these bins. This is 60, 65. Where will they lie? 50. What will this? Less than 60 will lie here. 65 will lie here. Right? In this way, I keep collecting and I keep building my, piling up my building. So let us say I get something like this. I don't think it will be very large. Okay. So this is a histogram. This could be number of people which have weights in these ranges. So let us say there are 50 people with this much weight, 45 people with weight in this range, only 10 people with weights in this range, like that. So this is called a histogram. Now this gives me an idea how will the PDF look like approximately. So let us say I model it with a Gaussian PDF. What is the meaning of Gaussian PDF? Okay, let us say first I try to model it with a uniform PDF. What is a uniform PDF? Uniform PDF means everything is constant in a particular range. Let's say maybe I will not take it completely there. I will just take it like this. This is 100. This is 25. This is probability of W. This is right. This is a uniform PDF. Is it a good model? Is it a good model? Question is it a good model? Please answer. Please answer on the chat window. Is it a good model to represent my data? No. Yeah, no. Very clear, right? Because the data is something like a hill and I'm modeling it with a plateau. That is not a good model. And how will you know, how will you quantify that this is not a good model? Tell me some intuitive way. I'm not going for a textbook answer. Intuitively, how can you tell, how can you quantify the goodness of this model? One way could be, if I convert this into a PMF, right? This is just numbers, and if I divide it with total number of observations, it will become a PMF. And this also can be discretized to form a PMF. And I take a KL divergence of that PMF. KL divergence. So for a bad model, KL divergence will be small or large. For a bad model like this, KL divergence will be large. Very good. KL divergence is kind of distance metric. It's a distance. So if two things are not similar, their distance will be large. So KL divergence will be large. So let me try to find out. So what are the parameters in the uniform distribution? The parameters are A and B, right? And height is 1 upon B minus A. So that the area is 1. This is just the uniform distribution. Now, what are the unknown parameters? The parameters are, if I select this model, my parameters are A and B. These are two parameters. Now, no matter, even if I have got many samples, if I estimate the values of A and B, I can never get a small KL divergence because the model is not fitting this distribution at all. Right? This is a very bad model in itself. Whatever values of parameters I estimate, they will never be able to represent the data faithfully. So what do I do? What do I do? I will choose another model. So this is the model selection. Model selection step. So this model is not good. What model can I choose then, which will give me some good results, which will give me some good modeling? Okay, somebody can say, I can simply choose this model, basically a PMF kind of model that I make small bins. Within each bin, I have a flat curve, and it's kind of uniform within this bin, but these bins have different probabilities. Right? That could be another model. It's a very good model, but it becomes intractable if the dimensionality increases. Here I have only single W, so I can make bins. Let us imagine if I have a 100-dimensional vector and I want to estimate its PDF. 100-dimensional vector, you discretize it and try to make bins. The number of observations will be very insufficient. You will not be able to model it very well. That is the limitation of this kind of bin distribution, or this kind of model. Now, one model which I can use is the Gaussian model. It has some mean and it has some variance or standard deviation. This is probability of W, and this is the random variable W. This is a Gaussian PDF, Gaussian probability density function. Now, what are the parameters here? Mu and sigma. These are the parameters of this distribution. And the next task is, given this data, I have to, okay, this was number 2 actually. Number 1 was data collection. Sample collection. This was number 1, first step. Second step was model selection. So I have selected my model. Okay, I selected Gaussian model. And it looks like this data shape And this data shape, or this model shape, is almost similar. So this model should be able to do a good job, right? So this model selection is done mostly manually. Nobody will train a machine, or machine can automatically choose a model. That is possible, but nobody does that generally. Generally, people, they choose the model intuitively or using their own analytics. Now the thing is, how do I estimate the parameters? So that was the topic of these lectures mostly. How do you estimate the parameters of a Gaussian distribution, right? This was a Gaussian distribution. How do you estimate the parameters given these samples? These are the weights, let us say, and you want to estimate the distribution. So we looked at MLE, maximum likelihood estimation, and we also looked at MAP, the maximum a posteriori distribution. Now, what is MLE? MLE means I want to maximize the probability of observing this sample set. See, T1 is S1, S1 is a sample, right? Sn is a sample. So we have total capital N independent samples or measurements. And T is the random variable. So what is the probability that the random variable is equal to first sample, second sample, and so on and so forth. And if I consider these as different measurements, so each measurement will be different instance of the same random variable, let us say, then what I want to maximize is the joint PDF, which is basically product of all the individual PDFs, because these are IID, identically and independently distributed. They are independent. That's why we can represent joint PDF as product of individual random variables PDFs. Okay, there are some questions. If dimension is high, as you explained, how can we be sure that certain model is suitable? Very good question. Yes, if the dimension is high, then I need a lots of data to train. Okay, if the dimension is high, model will have certain number of parameters, and if the number of parameters is, let's say, 10, I will need lots of data. I cannot have 10 samples to train 10 parameters, right? That will not be a good fit. If I have more number of parameters, then I need more number of samples. So if you read PRML, the introduction says a rule of thumb is that you need approximately 10 times the number of samples as compared to the number of parameters, scalar parameters. Because if a parameter is a vector, like if a mu is a vector of length 5, then it has got 5 scalar parameters to estimate. So when we talk of parameters, I'm saying what are the number of scalar parameters. Okay, so this is the thing. How do we know that the model is suitable? So I told you one method, very simple, we've discussed. We go back to it. KL divergence. So just like KL divergence is one metric, I can have more metrics also. I can have a metric of, as I mentioned here, log likelihood. Log likelihood. So log likelihood of P means I want to maximize the probability of observing those samples. Let us say I made observations. In my observations, there were out of 100. Let's go back to the example of heads and tails. Out of 100, I observed 99 heads and only one tail. Then will this PDF, this PMF, is this PMF a good fit for that observation? I have out of 100, I have 99 heads, one tail. 99 heads, one tails. Is this a good fit? Answer is yes or no. Please write on the chat window, no, yes. Okay, so you can tell it intuitively that yes, it is not a good fit. It is a very bad fit. But how do you quantify it? So you can quantify it using log likelihood. What is log likelihood? I think this is a good question, which who has asked? Piyush Gaurav has asked. It's a good question. Thank you for asking this question. How do we know how good is the fit? Very important question. So the answer is, out of many methods, one method which is very popular is log likelihood. Or let me first say only likelihood, because it's log of the likelihood is just log likelihood, but likelihood is the concept. So what is likelihood? Probability of observing that my x1 is a heads, x2 is a tails, x3 is again a okay, in our case heads. And so on. So out of 100 samples, I have 99 heads and 1 tails. Sorry, it should have been a round bracket because it's a joint PDF. This will be equal to probability of x1 equal to heads into probability of x2 equal to tails into so on and so forth. This is called likelihood. Now, imagine I gave, so if my probability of x is 0.4, 0.6, what will be this value? I will call it as L. What will be my L? L will be equal to probability of heads 0.4. Okay, tell me, let's see who answers quickly. Who answers first? What will be my likelihood? I think it should be more interactive so that you are getting the concept. It's very easy. Tell me what is the likelihood for the observation set where I have got 99 heads and only 1 tails. What is my L? Using this model. 0.4 times number of heads plus 0.6 times number of tails divided by 100. Not correct. 100 C99 0.4 to the power 99 times 0.6. Very good. 100 C99 may not be required here because these observations are all uh, 100 C99. 100 C99. 100. No, 100 C99 will not be there because these are all IID. The ordering is not important. The ordering is not important. Yeah, so 0.4 to the power 99 times 0.6. Yes. So if I just put the value, basically it's just putting these values here. Probability of x equal to heads is 0.4 into probability of x equal to tails is 0.6 into, like that it will go on, 0.4 into. So ultimately, you know, there are 99 heads. 0.4 to the power 99 into 0.6. That is the answer. This is the likelihood. Now consider another model. Consider this model where my probability of x is very large. Let us say 0.9, just to keep things simple. And this is 0.1. 0.9 and 0.1. This implies my L will be how much? Likelihood will be how much? Who can answer? I think it's very simple. Same way, 0.9 to the power 99 times 0. Now tell me which one is larger. Which one is larger? Which L is larger? Let me call this as P1x, P2x. This is L1, this is L2. Which one is larger? L1 or L2? Which is larger? Somebody said L2, somebody said L1, somebody said L2, L2, L1, L2. Okay. Oh, a lot of confusion. L1, L2, L1, L2. Okay. Let me do a PDF modeling for this data. How many people say L1 versus how many people say L2? It's really striking that people are having this confusion. Okay. I would say you use a calculator to find out these values. I think that will give you a good intuition. Please take out a calculator or your Python, open Python and do it. Let me do it myself. I think this is a good exercise. I think you can see the Python on screen. I will just say Python. It's Python 3. How will I do it? I will do import numpy as np. Now I will say np dot power 0.4. How much? 99 times 6. Oh, it's a really small number, 10 to the power minus 40. That is why we have got we usually take a log, because dealing with such small numbers, even our computers cannot do that, right? Our computers have finite precision. They will also break down. So, and let us take the other number, 0.9 to the power 0.99 times 0.1. Okay, now tell me which one is larger. Can you see the screen? I hope you can see the screen. Tell me which is larger. L2 is larger, right? It's 10 to the minus 6, while L1 is 10 to the minus 40. So I think, so because a large number to the power, to the large power, and versus a smaller number to the larger power, that makes the difference, right? If you take a large number and power is huge, compared to 99 values, this one value is nothing. So don't look at these values. These values won't play much role here. So 0.9 to the power 9. So, okay, which one is a better model? Clearly, this establishes L2 is larger than L1. So which one is a better model? This means P2x is a better model. P2x is a better model. P1x is not. Okay, can there be an even better model? The answer is yes. You can intuitively say, if I take this as 0.99 and this as 0.01, it will be even better model. I can show you. Let me take this 0.99 and this 0.01. This is just the estimation of P that we did before. You see, this is a 10 to the power minus 3. But you cannot go better than this. I mean, this is the best you can achieve, because this is, how you estimate it. This is called maximum likelihood estimate. So you estimated these values 0.9 and 0.99 and 0.01 using maximum likelihood estimate. These values of parameters, or the parameter P, This value of P maximizes my likelihood. This is the maximum likelihood I can obtain using this model type, the model type P1 minus P type. So this is why we say likelihood is a good measure of how good or bad is my model. Now, there is a question here. In binomial distribution, the basic assumption is that all the events are independent. So 100C1 should be multiplied in the previous example. Okay, we are not considering binomial distribution here. We are considering IID. All these observations are independent and identically distributed. Each individual observation is a binary distribution, but the what do you say? All the events are independent, right? So this is different from a binomial distribution. The whole thing might be binomial, but we are not modeling it as a binomial. We are modeling each individual uh, uh, observation or each individual random variable as a binary distribution. How likelihood is different from probability, or can we say they are same? So likelihood is probability of the likelihood is the joint probability basically. Likelihood is the joint probability of observation. So this is the joint probability of all the observations or samples. This is a joint probability of all the observations. That is likelihood. And you want to maximize it. Maximum likelihood tells you the best model. Is this clear? I think this was a very good point. That is why we come here to this estimate. That to estimate my mu and sigma, I am maximizing my likelihood, but I take a log of this for obvious reason. As I showed you, the values become so small, 10 to the minus 40 and so on, just for 100 observations. But imagine if you have thousands or millions of observations, the values will be even smaller. So that's why we take a log, so that thing becomes manageable. The precision becomes manageable. Because if you take a log, minus 10 to the minus 40 will simply become of the order of minus 40, which is a very small, which is a very manageable value. So that's why so here we want to find the parameters of the model which are maximizing the likelihood of observing these samples, or the probability of observing these samples, the joint probability of observing these samples, which is called the likelihood. Now we take a log, so that for numerical convenience as well as computational convenience, you will see computations become very easy with the help of this log, because log is a monotonic function, monotonically increasing function. So wherever the maxima of P is occurring, the maxima of log will also occur there, right? Because it's a monotonically increasing function. Okay, now somebody asked the question, what is the meaning of argmax? The meaning of argmax is, if I simply say max, if I say max of this function, this will return me the maximum value of this function, which will be, let us go back to our Python thing. The maximum value of that function is simply 0.00369, right? So we don't want the maximum value of the function and assign it to the parameter. We want the values of parameters which are maximizing this function. So this function is maximized for a particular mu and sigma. So argmax means the values of those arguments which maximize this function. What are those arguments? Mu and sigma. The values of the arguments, whatever is written in the bottom, mu and sigma, which maximize this function, that value should be returned, and that is assigned to mu and sigma. Think it in terms of computer programming. That is also very much like mathematics. So Is this clear? This argmax is, it does not return the maximum value, but the value of arguments which maximize the function. And there are mathematics. I hope you have gone through it. I think once you understand the intuitive understanding, these mathematics become very easy. This is maximum likelihood estimate. And then if you have prior belief, then you go for maximum a posteriori estimate. Maximum a posteriori estimate means you have some prior belief and you are adding it on top of your existing thing. Let us say if I already have an intuitive idea, people will have a weight of, let's say, about 60 with a variance of about 10, or the standard deviation of about 10. That is my intuitive model, which I already have in my mind. So I'm also adding that. So what is the benefit it brings? So the first benefit is the number of samples which I require for an efficient estimation of the parameters. That sample requirement reduces, because I already have told start from here. Little bit fine tuning is required, little bit adjustment is required. So you can make it faster. The estimation becomes more faster, means with less number of samples you can estimate better. That is the advantage of using some prior estimate. Okay. Now we have map estimate is in this way. And then we say, what if the random variable also are, random variable themselves are the parameters themselves are a random variable. If the parameter of a PDF of a random variable itself is a random variable, what happens? So it means, okay, my mu or my parameters don't have one particular value, but they have a distribution. Okay, let us say my mu has a Gaussian distribution with this much variance and this much mean. So that is the idea of Bayesian estimation of mu. I think we can stop here. The remaining 2 lectures also deal with different aspects of estimation. We study Gaussian distribution, we study Gaussian mixture models and things like that. So, but the basic idea, I think if you understand this, the basic idea will be very clear.
Sir, I have a question.
Please.
Sir, Piyush here. Sir, if in a map estimate, if suppose we multiply with prior, so the output won't be a Gaussian in that case. So are we estimating it to be a Gaussian, or how are we going about it?
Okay, good question. So if my prior is also a Gaussian prior, and my model is also a Gaussian model, then my posterior will also be a Gaussian. That's what we also prove here in these slides. And if my prior is a Gaussian prior and my model is also Gaussian, then the posterior will also be a Gaussian. Is that clear?
Okay, okay.
Yeah.
But
so these,
essentially both prior and the probability should be Gaussian.
yes, the likelihood and the prior both should be Gaussian. Then my posterior will be also Gaussian.
Okay, thank you.
These distributions are very special, where your posterior and a prior. No, sorry, this was not the. This is not likelihood. This is the prior. Sorry, this is the prior. This is likelihood. Where my prior and posterior both have same distribution. These distributions are priors are, maybe they're called conjugate priors. I forgot the name exactly. Maybe conjugate priors or something they're called, where basically my posterior and prior both have same family of distribution, same distribution. Gaussian is one such example. Okay, I think we can stop here. It's a little bit more than 3 p.m. Thank you very much.